In this problem, we're given a function. This is a function involving a trig function involving cosine. So it's saying that we're only going to consider this function over the interval as x goes from 0 to 2 pi. And first, we're supposed to find any intervals on which f of x is increasing and decreasing, and then any local minimum or maximum values of f of x. When I find where the function is increasing and decreasing, that's actually going to help me find any local minimum and maximum values. Because what I can look at there is, if it changes from increasing to decreasing, well, increasing is going up, decreasing is going down, that would be a maximum, right? So if it's increasing and then decreasing, I'd have a lower relative max. Whereas if I change from decreasing to increasing, that would be a relative minimum value. It doesn't like that. Okay. So we need to decide where this is increasing or decreasing to do the whole problem. And increasing or decreasing, the way I get that information is by looking at the first derivative. If the first derivative is positive, the function is increasing. If the first derivative is negative, then the function is decreasing. So I'm going to look at f prime of x. Now, if I take that derivative, the derivative of x is just 1. The derivative of 2 times something is 2 times the derivative of something, so 2. And then the derivative of cosine is negative sine. So I get 1 minus 2 sine x is my derivative. What I want to do is I want to set that equal to 0. So I'm going to get 1 minus 2 sine x equals 0. So that would say 1 equals 2 sine x. Or that would tell me that sine x has to equal 1/2. Okay, now to figure out where sine is 1/2, we may have to think about, again, the unit circle a little bit. So 1/2, we had those special angles, especially 30 degrees and 60 degrees, or pi over 6 and pi over 3 in radians. Those were the ones that had the sine or cosine was 1/2, and the other was square root of 3 over 2. Remember, sine is the y-coordinate on the unit circle. So 1/2 is smaller than square root of 3 over 2, so that means here my y-coordinate is less than my x-coordinate. So that's going to have to be really then pi over 6. That's going to be the angle that I want here to have a sine equal to 1/2. But where else is the sine positive? The y-coordinate's also positive in the second quadrant. So I would need something over here that would have the same reference angle of pi over 6. If I go all the way over, of course, that's pi, which would be 6 pi over 6. So the angle I want here, then, if I come back 6, I get 5 pi over 6. That was sort of messy there, huh? So I get 5 pi over 6. And so my solution then, I would have x is equal to pi over 6, or x is equal to 5 pi over 6. That's where I'm going to get a sine equal to 1/2 for what I'm doing here. Now, if I'm going to divide this into intervals to decide where it's positive or negative, then I'm starting at 0. We have pi over 6. We have 5 pi over 6. And at the very end over here, we would have 2 pi. So I get intervals around those points. So I'm going to look at an interval. I'm going to take a test number. And then I'm going to look at the derivative, which is 1 minus 2 sine x. So I'm going to have from 0 to pi over 6. We're going to have from pi over 6 to 5 pi over 6, and then from 5 pi over 6 to 2 pi. Now, for a test number, we're going to have to evaluate this derivative for some values. We can, of course, use a calculator. If you want to use your calculator, it may be easier here to think of this in degrees. So we may want to think of this in degree mode and put your calculator in degree mode to calculate this. Between 0 and pi over 6, well, we don't have any standard angles between there. Pi over 6 is 30 degrees. If I cut that in half, something between 0 and pi over 6, over here on the unit circle, that's 30 degrees, so half that would be 15 degrees. Half of pi over 6 would be pi over 12. So my test number could be pi over 12, but that's the same thing as 15 degrees. What I can do then is I can put that in a calculator, take 1 minus 2 times the sine of 15 degrees, and if you do that, you get positive 0.48. And all that's really important is that that's positive. That means my first derivative is positive, which means my function is increasing. There. Between pi over 6 and 5 pi over 6, that's between 30 degrees and 150 degrees. Right in between there, I would have pi over 2, which is 90 degrees. Of course, the sine of 90 degrees, if I plug that in, the sine of 90 degrees is 1, right? The sine would be the y-coordinate of 90 degrees up here at the top. So I get 1 minus 2 times 1, that's 1 minus 2, which gives me negative 1. The only important thing there really then is that it's negative, so my function would be decreasing there. And then between 5 pi over 6 and 2 pi, well, I have a lot of stuff in between there, right? From 5 pi over the 6 all the way to 2 pi would be over here. I could just take pi, right? That's right after 5 pi over 6. Of course, pi is equal to 180 degrees. The sine of pi, the sine of 180 degrees, well, that's the y-coordinate on the unit circle here, which would be 0. So I would get 1 minus 2 times 0, or you can do this on a calculator. We would just get 1, so that's positive, so this is going to be increasing there. So where's my function increasing? Where's my function decreasing? It's increasing here and here. So that's from 0 to pi over 6 and from 5 pi over 6 to 2 pi. Where my function is decreasing, well, I only have one interval there, that's in the middle, so that would be from pi over 6 to 5 pi over 6. So what about relative, that's where it's increasing and decreasing. That's the first part of the problem. Then I'm supposed to find any relative minimum or maximum values. So minimum and maximum values, remember, is where the function changes from increasing to decreasing or decreasing to increasing. So from 0 to pi over 6, it's increasing, so the function's going up, but then it starts decreasing at pi over 6. So at pi over 6, it changes from increasing to decreasing. That's a relative max, or a local max. So we have a local max at x equals pi over 6. Then here it changes from decreasing to increasing at 5 pi over 6. So that's going to be a local min. So that's at x equals 5 pi. Nice pi there. But those are not the actual local minimum and maximum values. Those are the x coordinates where they occur. So I have to go back to the original function to find the y coordinates. Those are the actual values I need. So I need f of pi over 6. So if I plug that in to my function f up here, I'm going to get pi over 6 for x plus 2 cosine pi over 6. Well, the cosine of pi over 6 is over here. The sine there was 1/2. The cosine is going to be square root of 3 over 2. So that's going to be pi over 6 plus 2 times square root of 3 over 2, or that's just going to be pi over 6 plus the square root of 3. And if we look at that, that's approximately, on a calculator, 2.26. And then if I look at, and that's my pi over 6 is my local max. To find the minimum then, I have to look at f of 5 pi over 6. So that's going to be 5 pi over 6 plus 2 times the cosine of 5 pi over 6. Now the cosine of 5 pi over 6, 5 pi over 6 is over here. Its sine was 1/2. Its cosine is going to be the x coordinate, which would be square root of 3 over 2. But since it's in the second quadrant, it's going to be negative square root of 3 over 2. So I'm going to get 5 pi over 6 minus the square root of 3. If I do that on a calculator, that's approximately 0.89. And that's my local minimum. So that's the first part of the problem. We've figured out where it's increasing and decreasing. We've found local minimum and local maximum values. Now, if I go to the next page, we're supposed to find where this is concave up and concave down. To find where the function is concave up and concave down, I need to look at the second derivative. And so I look here, just what we'd had before. This was, got a little messy in my notation there. This was the first derivative, so I'm just going to have to take the derivative of that. So I'm going to get the second derivative, f double prime of x. Well, the derivative of 1 is just 0. The derivative of sine is just cosine. The negative 2 is going to go along for the ride. So I'm just going to get negative 2 times the cosine of x for my second derivative. We set that equal to 0 then. And when I divide by negative 2, then that tells me cosine x has to be 0. When I think of the unit circle, cosine is the x-coordinate on the unit circle. So if I want an x-coordinate to be equal to 0, that's going to be along this line here. So I'm going to get up here and down here is where I'm going to have x-coordinates equal to 0. So up at the top, that's x equals pi over 2. And at the bottom, that would be x equals 3 pi over 2. So those are my candidates. That's where the second derivative is equal to 0. So where it's going to be concave up and concave down would be at intervals around those points. So we're starting at 0 and going to 2 pi. Pi over 2 is in here somewhere. 3 pi over 2 is over here somewhere. Of course, pi is right in the middle there. So my intervals that I get from 0 to pi over 2. I get from pi over 2 to 3 pi over 2. And I get from 3 pi over 2 to 2 pi. And I'm going to make my sign chart. So I have my interval. I'm going to get a test number in each interval. And then I'm going to have to look at my second derivative, which here it's pretty easy, just -2 cosine x. So 0 to pi over 2, pi over 2 to 3 pi over 2, and from 3 pi over 2 to 2 pi. Those are my intervals. For a test number, 0 to pi over 2, and pi over 2 is up here at 90 degrees, so between that would be 45 degrees, which is pi over 4. If I take -2 times the cosine of pi over 4, that's going to be -2 times the cosine of pi over 4. Well, the cosine of pi over 4, that's in the first quadrant, so the x-coordinate is positive. So the only important thing there is that it's negative. So that's going to be concave down. Between pi over 2 and 3 pi over 2, well, right in between there would be 180 degrees, or pi. And you can calculate this second derivative by hand, or you can use a calculator. -2 times the cosine of pi, or -2 times the cosine of 180 degrees. The cosine of pi, that's the x-coordinate over here, that would be -1. So I would get -2 times -1, that's equal to +2, so that's going to be positive. So it's going to be concave up. And then from 3 pi over 2 to 2 pi, I'm going to need an angle in here. Again, I could do 45 degrees. 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4. That would be 7 pi over 4. That's a 45-degree reference angle, so 360 minus 45 would be 315 degrees, or 7 pi over 4. So I would get -2 times the cosine of 7 pi over 4. And you could do that on a calculator or do whatever. It ends up being negative. So that's where it's concave down. So where is it concave up? That's from pi over 2 to 3 pi over 2. Where is it concave down? Well, those are the other ones, from 0 to pi over 2, and from 3 pi over 2 to 2 pi. Do we have any points of inflection? Well, points of inflection occur where it changes from concave down to concave up, or from concave up to concave down. And so we see here that happens at pi over 2, and it happens at 3 pi over 2. But it says I need the points, the coordinates of any points of inflection, so I need the y-coordinates. Remember, for the y-coordinates, you have to go back to the original function. So I'm going to have to do f of pi over 2. So that's going to be pi over 2 plus 2 times the cosine of pi over 2. Well, cosine of pi over 2 is up here on the unit circle. Cosine is the x-coordinate, and that's going to be 0 there. So 2 times 0 is 0, so f of pi over 2 is just pi over 2, right? Because this cosine pi over 2 is equal to 0. And then if I do f of 3 pi over 2, the same sort of thing happens actually. So I get 3 pi over 2 plus 2 times the cosine of 3 pi over 2. But again, if I think of that 3 pi over 2 is down here, the x-coordinate is still 0. So I just get 3 pi over 2 back. So my points of inflection, I plugged in x equals pi over 2, I get out y equals pi over 2. I plug in x equals 3 pi over 2, I get out y equals 3 pi over 2. So my points of inflection are pi over 2, and 3 pi over 2, 3 pi over 2. And that's the problem. Just to see how this sort of works and see that it does that okay, if I look at a graph of this, I've done the graph here. Here's a graph of the function. Notice, we found out that this had a local maximum at pi over 6. Pi over 6 is about 0.57, so it would be a little over a half. That's up here where it hits there. My local minimum was at 5 pi over 6, that's right here. And these were the inflection points. Notice it's concave down, and then it changes to concave up, and then somewhere here again it changes to concave down. Notice that you might say, well, wait a minute, this is a local maximum and we didn't find it. Well, that actually comes after 2 pi. 2 times pi, 2 times 3.14 would be 6.28, which would be in here somewhere. We don't quite get to that point there yet, okay? Where that would be, it would be at 2 pi plus this pi over 6, so 2 pi is 12 pi over 6. This would occur at 13 pi over 6, whatever that would be. That's where that other local maximum occurs. But we're only talking about just a portion of this graph, and those are the key points that we've just found.